Today we're going to talk about how things dissolve. You have notes for this. We started this in class after our quiz. They're called Lesson 2.1, General Properties of Aqueous Solutions. In order for something to be aqueous, it has to dissolve in water. So we're going to divide our aqueous solutions into two types to start with. The first one is an electrolyte. An electrolyte is a solution that conducts electricity. Electrolyte, it conducts electricity. This solution is an electrolyte because you see the light bulb is on. This solution right here has some sort of salt in it, some sort of ionic substance, actually it's sodium chloride, and it is conducting electricity. We will learn in a few minutes that you can have strong electrolytes, this one looks strong, or weak. As you might have guessed, a non-electrolyte is a solution that does not conduct electricity at all. And these two solutions are non-electrolytes. No, the light bulb is not on, even though the probes are in water. They are not conduct. This is pure water. It does not conduct electricity. Pure water is just water with nothing dissolved in it. In this case, they're putting, I'm pretending they're putting propane in. They're actually putting sugar in, but I learned last year sugar actually does conduct electricity a little bit. It is a weak electrolyte. This is a bad example for this textbook. But there are things that are non-electrolytes. They have to be covalent substances. Propane would be a non-electrolyte, something that does not conduct electricity. We're going to talk about a few definitions. A polar substance is something that is unbalanced in charge. Unbalanced in charge. So that would be, an example of that would be a water molecule. I'm going to draw a little water molecule here. We have oxygen, and these are the hydrogens. And because oxygen is more electronegative, which means it holds on to the electrons more than the hydrogens. I can't remember if we talked about that next year, but if we didn't, I'm introducing it now. I'm going to write that word down. As I was writing, I remembered we did talk about this last year when we talked about periodic trends. Fluorine is the most electronegative atom on the periodic table. Oxygen is pretty close to fluorine, which means it really is very greedy. It holds on to its electrons. It's going to have two lone pairs over here also, because hydrogen is bonding with the oxygen. That's my little purple line, 2 electrons for each line. But these electrons here are not equally shared between the hydrogen and the oxygen because the oxygen has more pull for them. What you end up with then is a slight positive charge on each of the hydrogens and a slight negative charge on the other side of the oxygen. So water is polar, unbalanced and charged, more negative on this side, more positive on this side. It is polar. As you can possibly guess, nonpolar would be the opposite. It is something that is balanced in charge. An example of something that is polar, an example of something that is nonpolar would be methane, right? CH4. This is very even though the sharing of the electrons are very equal around the carbon atom. So this is a nonpolar molecule because even though carbon may be holding on to more of these electrons than the hydrogen, and actually they share them pretty equally. Carbon and hydrogen are almost equally electronegative. So this is a very balanced molecule, and therefore it is nonpolar. We can look at a table, and we will later in the year, of electronegativity. But one way to tell that this is nonpolar is that it looks pretty balanced when you draw the Lewis structure. In this unit, we're going to be focusing more on polar substances. Polar substances dissolve other polar or ionic substances, and we're going to talk about ionic in a second. So there is a phrase called like dissolves like. It won't get you any credit on the AP exam, so don't use it. But what it means is polar substances will dissolve other polar or ionic substances. and I'm going to talk about that in a second. And nonpolar substances will tend to dissolve nonpolar substances. The short way is to explain it as like dissolves like, but you on the AP exam will have to give more detail. We're going to come back to that in a second. Ionic means made of ions, and hopefully you remember what an ion is. An ion is an atom that has lost or gained electrons. Oops. And so my page is getting too messy, so I made it smaller. So ionic substance, an ion, let's say a sodium ion. Sodium starts out with 11 protons in its nucleus, and it starts out with 11 electrons on the outside. But when it becomes an ion, it loses one of these electrons, gives it away to something else, and it ends up with, still has the 11 protons. You never lose your protons, but now it only has 10 electrons, which means a sodium ion has a positive charge. A molecular substance does not form ions. Okay? A molecular substance does not form ions when it is dissolved. Stays as molecules. And hydrogen bonds, let's talk about that on the next page. Actually, I'm going to change this definition for right now. Cross out hydrogen bond. We'll come back to that. Hydrogen bond is a type of dipole-dipole force, so write that in instead. Dipole-dipole force. Okay, I showed you this in class. I'm showing it to you again. It's a very important picture. This solid is meant to represent a sodium chloride crystal, a solid. The green things, the bigger ions, the green ones, are the sodiums. The purple ones are the negative chloride ions. This sodium ion crystal has been put in water. These little red and white things are meant to be water molecules. When something dissolves in water, the water molecules attack the substance, and through electric attraction, electrostatic it's called, but it's basically electric, they remove the ions. So each ion ends up being surrounded by water molecules. What happens is, this is my picture of a water molecule. The negative side of the oxygen is attracted to the positive, where are they? Wait a minute, let me think of it. Why is the, oh, I made it. Actually, when they're ions, the size of the chloride ion is bigger than the size of the sodium ion. We'll talk about that later. The negative oxygen, the red part, is attracted to the positive sodium, and it rips it apart. And you have an electric attraction between the negative oxygen here and, I'm going to do it as purple, the sodium ion. That's this dot. And this is this dotted line. My drawing's getting a little sketchy. This is a electric attraction. Electric. It's really electrostatic. And we call this attraction between the negative oxygen and the positive sodium a dipole-dipole force, because pole refers to electric. So this attraction here is a dipole force. It's not as strong as a bond, but it is a type of intermolecular force, which we have mentioned before, and it holds the water and the sodium together loosely. And that's how things dissolve. There is a loose attraction between the water and the sodium, and that attraction is stronger, or the way the energy works out, that attraction ends up being more favorable or more stable than the attraction that was here when it was with the chloride ion. So there's energy involved here. On this side, we have a molecular substance. This gray and white thing is meant to be the molecular substance. It's methanol in this case, which is an alcohol. And it is dissolving, which means it's being attracted to, and there is an intermolecular force between this methanol molecule and this water molecule. This is not a dipole-dipole force. Actually, this might be a dipole force, because there may be a slight electric attraction here, depending upon the polarity of methanol. Methanol is going to be slightly polar. So there's still a dipole-dipole force here, but it's not the same as this one. We're going to talk more about dipole-dipole forces in future units. But what I want you to start to understand is that when it dissolves and the sodium ion or the chloride ion is surrounded by water molecules, that arrangement is energetically more stable. These attractions are really more powerful or more stable than when it was in this arrangement. And if something doesn't dissolve, that means it's more stable when it's a solid. So we're going to be continuing to talk about that. So I'm going to make this video 1.5 minutes longer. I'm going to talk about how ionic compounds dissolve and how they conduct electricity. And I'm specifically going to talk about strong electrolytes, which are the notes below this picture on your paper. So you have words, it says strong electrolytes, and then you have examples. And it says, where's my pen? NaCl. So when something like NaCl dissolves in water, that is an ionic compound, and it's a solid, and we're going to put it in water, so I'm just going to write the water up here. It will, as we saw in the picture before, break up completely into sodium ions and chloride ions. And I've put this AQ here. That means these are aqueous. They're dissolved. That's what the AQ means. It's dissolved. So sodium chloride will break up completely when it's in water into sodium ions and chloride ions. And it is these ions that conduct the electricity. So I've drawn a picture of a circuit here. This is my negative probe, my positive electrode. Here's my light bulb. And we've put the two electrodes into water. And this is a strong electrolyte, so this light bulb will light up. Electrons are not moving in the water. It's not electrons that are moving. There are no lone electrons floating around in here. See this E with this? This is not floating around all alone by itself, crossing it out. What carries the charge is that these charged ions, the chloride ions, flow over here to the positive side, and the positive ones are attracted over here. And then once they get, we'll talk about this more at the end of the year, but once they get here, then electrons do flow through the wire. But what's happening in the water is that the actual charged ions are moving towards the probes. So this was one example of how to draw an equation, how something dissolves. We're going to do one more. I realize I went on a little long. I'm going to dissolve calcium hydroxide in water. So this calcium hydroxide is a solid, but I put it in water. The water is over the arrow, and it's going to break up into a calcium ion, so Ca+2, aqueous, and it's going to break up into two hydroxide ions, two OHs. See the subscript 2? This will completely disassociate into two hydroxides. Let's draw a picture. This is my picture of calcium hydroxide. I have a calcium ion here, and I could put a +2 charge on it. And I have two hydroxide ions. One is here. I'm going to circle it in black. So this has a -1 charge, and one is here. Now when I put this whole thing in water, it's going to break up into ions. There's only one calcium ion here, so it only breaks up into one calcium ion. But there are two of these hydroxide ions, which is a polyatomic ion made of OH. So it breaks up into two hydroxide ions, and that's how I would draw that in pictures. So we're going to work on that more in class. Now you may watch the video on precipitate reactions.